Okay, our next example, we will now be looking at DC motor analysis with armature reaction. Previously, all the example 1, 2 and 3, we assumed there was compensating winding, so there's no armature reaction, but this time we will see what happens when there is armature reaction. So in this example, we have a DC motor, which is again the 150 volt separately excited DC motor. We have the same parameters, RA 0.2 ohms, the field winding with 1800 turns, the field resistance of 100 ohms, the adjustable resistance which can be changed from 0 to 300 ohms, the field winding voltage of 180 volts, and the same magnetization curve at the speed of 1500 rpm. However, this time, it's mentioned in the question, armature reaction causes the DC motor to experience a demagnetizing MMF of 180 ampere turns. Now, we'll talk about this demagnetizing MMF again shortly. So, what is asked in the question, if the adjustable resistance is set at 200 ohms, we want to calculate the no-load speed of the DC motor and the speed of the DC motor when the line current is 90 amperes. So, to summarize the information from the question, we have these parameters Vt of 150 volts, Ra, Nf, Rf, and Vf. And the extra information compared to all the other examples, we have a armature reaction demagnetizing MMF, which is denoted as FAR. Remember, F is MMF, AR for armature reaction. So the demagnetizing, I'm going to write it here. FAR is the demagnetizing MMF due to armature reaction, AR. And the value of the demagnetizing MMF is 180 ampere turns. Now, what we want to do is we want to find the no-load speed and the speed when IL is 90 amperes. 90 amperes, I'm sorry for the mistake here. 90 amperes. And in both conditions, the R adjustable is set to be 200 ohms. So in order to start our analysis of the DC motor, previously we mentioned that we need three tools to analyze the DC motor: the equivalent circuit, the equations for the equivalent circuit, and the magnetization curve. Now that we have armature reaction, there's another extra information that we need. Now, as we've seen previously, armature reaction causes flux weakening, and the weakening of the flux, this only happens when there is a load connected to the motor, meaning this only happens when IA is not equal to 0. So the flux weakening means there is a demagnetizing MMF, and that we put the symbol FAR. Now, a demagnetizing MMF means what the machine or the motor sees is an effective field current. And to calculate this effective field current, IF star, we must use this equation. IF star is the actual field current, IF is the actual field current, minus the demagnetizing armature reaction, F armature reaction, FAR, and we must divide this by NF, where NF is the number of turns of your field winding. So the effective field current must be calculated, and we will then use this effective field current to read from the magnetization curve. So in order to continue with this example, we need information of the demagnetizing MMF, and this is required in order for us to calculate the effective field current. So let's go back to the example. Now we're back to our example 4 of a DC motor with armature reaction, and what we want to do is we want to calculate the no-load speed and the speed at a certain current condition. Now we've already previously seen armature reaction causes a demagnetizing MMF, so this is where the calculations will be different compared to the previous examples. Now from this example 4 question, we already have the parameters of the DC motor, VT, RA, RF and VF. We also have the NF, which is the number of turns of your field winding, which is important now in this question. And the extra information for armature reaction questions is the armature reaction causes a demagnetizing MMF. We call that FAR, and the value is 180 ampere turns in this question. So what we want to do, we're going to calculate the no load speed. That's what they want to find. If R adjustable is set at 200 ohms, what is the no load speed? Okay, so at no load, we already know the induced torque is equal to 0, and therefore IA no load is equal to 0. And from the equivalent circuit, the KVL of the armature side states that EA is equal to VT minus RAIA, and since we're considering the no load condition, so everything must be at no load, and since IA no load is 0, so therefore EA no load is equal to VT no load, which is 150 volts. Now we also know from the equations of the DC motor that EA is equal to K flux omega, and thus the omega no load is EA over K flux, which is 150 over K flux. Now we can't solve this yet to find the no load speed because we don't have the information of K flux. So we must use some other condition to find K flux, and then we can calculate the no load speed. In order to do that, we must calculate the field current. Now, for a separately excited DC motor, field current is VF over RF plus R adjustable. And in this question, VF is 180, RF is 100 ohms, and R adjustable is 200 ohms. So this gives us a field current of 0.6 amperes. For armature reaction to happen, from our previous knowledge, armature reaction only happens armature reaction only happens when IA is not equal to 0. So what is very important here, at no load, there's no armature reaction. So therefore, the effective field current will equal IF at no load. And therefore, IF star is equal to IF, which is 0.6 ampere in this question. And from table 1, which is the magnetization curve, when IF is 0.6, when IF star is 0.6 amperes, the EA0, as you can see in the table, is 102 volts at a speed N0 of 1500 RPM. And from this information, we can get K flux, since EA0 is equal to K flux omega 0. So K flux is 102 divided by 1500, but this must be changed to radians per second since we're talking about omega. So we must multiply 2 pi over 60, and we get a K flux value of 0.649. So substituting the value of K flux into our equation for no load speed, we'll get 150 divided by 0.649, which comes out to be 231.12 radians per second. So this is the no load speed. So the most important thing that I want to highlight at this part of the no load speed is the no load speed is not affected by armature reaction because the armature current is equal to 0 at no load. So this is a very important point that you must be able to understand. The no load speed doesn't change because there's no armature reaction at no load. So now let's move on to the second part of this question. So in the second part of this question, we want to calculate the speed of the DC motor when the line current is 90 amperes. And don't forget, in this part, this example, armature reaction is causing a demagnetizing MMF of 180 ampere turns. So we know that R adjustable is set at 200 ohms. The line current is 90 amperes. So we want to know what is the speed of the motor. So in order to start this part of the question, we need to find the armature current, and from the separately excited DC motor equivalent circuit, IL is equal to IA. Okay, remember we are a separately excited DC motor. So therefore IA is equal to IL, which is 90 amperes. And then from the KVL equation of the armature circuit, EA is equal to VT minus RAIA, substituting the value of VT 150, RA 0.2, and IA of 90. We get the EA to be 132 volts. Now we know that EA is equal to K flux omega, so therefore the speed is EA divided by K flux, 132 over K flux. Now remember, armature reaction is present in this motor. So what we need to do, in order to evaluate what happens with armature reaction, from the field current, we will then after this have to find the effective field current. So first let's find the field current IF, which is VF over RF plus R adjustable, and it will come out to be 0.6 amperes. We've done this many times. But due to armature reaction, the effective field current IF star, the formula is IF star equal to IF minus the armature reaction demagnetizing MMF over the number of turns. So let's calculate this IF star for this motor. IF star is IF 0.6, the armature reaction demagnetizing MMF, which is 180 ampere turns, and the total number of turns is 1800. So IF star comes out to be 0.5 amperes. So where is this IF star going to affect our calculation? We need to use IF star to read the table or the magnetization curve. So instead of using IF with armature reaction, we must read at IF star. So when IF star is equal to 0.5 ampere, from table 1, EA0 is 93 volts at N0 of 1500 RPM. So from here, K flux is 93 over 1500 times 2 pi over 60, and the K flux with armature reaction is 0.592. So the difference in all the previous examples, to read the table we use IF, but when there's armature reaction we must read the table at IF star. And the same goes if you have a graph. We read the graph at IF star value. So therefore, substituting equation 2 into equation 1, we can calculate the speed of the motor at 90 amps line current. 132 divided by the new K flux due to armature reaction, 0.592, and this gives us a speed of 222.97 radians per second. Right, now what I want to do is just to put all things in perspective, starting from example 1 until example 4. So in example 1, there was no armature reaction and R adjustable was set to 200 ohms, and we got a no load speed of 231.12 radians per second. In example 2, there was also no armature reaction. R adjustable was set to 200 ohms and a line current of 90 amperes was given, and the speed of the motor was 203.39 radians per second. At this line current of 90 amperes, in example 3, the same condition, no armature reaction, R adjustable was 200 ohms, line current was 90 amperes, and we found that at this speed and this line current, the induced torque was 58.42 Newton meter, and the efficiency of the machine was 79.11%. So what we did, when we plot this speed against induced torque, at no load, the torque induced is 0, so the no load speed is 231.12 in radians per second for this machine, and as the torque increased to 58.42 Newton meters, the speed of the machine became 203.39. So this information or this graph is all obtained from example 1, 2, and 3. And during this time, there was no armature reaction. So if you remember, this graph is what we call the terminal characteristic of the DC motor, or it's also called a graph of speed against torque. Now in example 4, we had armature reaction which caused the demagnetizing MMF of 180 ampere turns. The adjustable resistance was set at 200 ohms still, and at no load, let me write it again. At no load, the speed was still the same, 231.12 radians per second, the same as in example 1, but when IL was changed to 90 amperes, with armature reaction, the speed with armature reaction became higher than example 2, which is 222.97 radians per second. So with armature reaction, for the same line current, comparing example 2 answer and example 4 answer, the speed with armature reaction has increased. Now this is as expected. Remember, armature reaction causes flux weakening. And for the same load, IL value or same load, the EA was 132 volts, but because the flux is reduced, the speed will increase when there's flux weakening. So if we were to plot this on the graph, 200, so as the no load speed is the same, but as you increase the speed, as you increase the load, the armature reaction will cause the speed to first reduce, but then increase again when there is armature reaction, and the final speed was 222.97. So with armature reaction, the terminal characteristic of the DC motor would start off going down, but then it will curl up due to the armature reaction. So this is how the terminal characteristic will differ between a no armature reaction case and a case with armature reaction. So please pay attention to this. The same characteristic happens for both the shunt and the separately excited DC motor. So the graph is the same whether you are a shunt or a separately excited DC motor. If there's no armature reaction, the terminal characteristic is just a straight line going down, but once there is armature reaction, the speed will tend to curl up as you increase the torque. And why the speed increases as the torque increases? Because the flux weakening in armature reaction causes the flux to be less and the speed will increase when load increases. So this is the end of the example for separately excited DC motor. You can have a look at it many times. If you still have questions on this example, you can come and see me at my office. Thank you.